presentation will be performed by Tittu Varghese Mathew. I hope to pronounce it clearly. And Mr. Mathew is a Bachelor in Mechanical Engineering from India, and he received a Master in Aerospace Engineering in Netherlands. At the time being, he is working at the Delft University. His specialization are MEMS, micropropulsion, space propulsion system, and space system engineering. Please, Mr. Mathew.
Thank you very much for the introduction. Well, first of all, I would like to apologize for the delay, but I'm not here to give any apologies. I'm here to present my paper on my master thesis research work, which I did at Delft University as part of my master thesis. And so, through this, during this presentation, I would like to take you through an introduction of my work, and secondly, the design of my thruster design, and thirdly, the fabrication that we use for fabricating the thruster, and finally, the test results that we achieved, the first test results, and then the conclusion. So, we all know that the space community is giving a lot of importance on nanosatellites because of its low mass and less launch cost. So for any nanosatellite to put in space and to have some kind of mission capabilities, it needs some kind of a propulsion system. So the Delft University has been investigating on cold gas propulsion systems for the past 45 years. And the system shown here is called the T3 micropropulsion system because it was developed in a collaboration between the TUDelft, U20, and the TNO company in the Netherlands. And this makes use of cold gas nitrogen stored at a high pressure of 5 bars, and it is just expanded through this MEMS nozzle. And this system is currently in testing phase, and this will be later on used in this Delphinex satellite platform, which is a student microsatellite design at Delft, and it will be launched in 2012. So, okay, the cold gas micropropulsion system is quite simple in its system architecture because it just requires a propellant tank which can store gas at a high pressure and then expand the gas through a nozzle. But it has a limitation because it has got a very low specific impulse. As a result, due to its low exhaust velocity, it cannot be used in high delta V emissions like in the range of 50 to 100 meters per second. So we need to think about a different option. How can we achieve a high exhaust velocity? And one of the means was to come up with a resistojet concept, which is the next step. Now this is a schematic diagram of the device which we made, and this basically consists of the silicon on top, and which is bonded by a Parex glass at the bottom, and it is heated by a heater layer which is made of aluminum. It's deposited on the top of the silicon, and this aluminum is heated from using an external power source, and that in turn heats the propellant which flows through the microfluidic channels which is etched in the silicon. I will explain that later in detail a little bit later. So the resistor is quite simple in design. It needs a heater to heat the propellant flow by forced convection and then expand the flow to produce through a nozzle to produce a thrust. And the thrust range we are aiming is a little bit of 1 millinewton and lower in order to make it applicable for the orbital maneuver of nanosatellites in space. And what are the advantages of resistojets compared to all other kind of research work done in ion thrusters and cold gas? So one of the advantages is that it's high thrust to power ratio because the ion thrusters requires a huge amount of power to produce the required thrust. And secondly, it comes to the lower system mass because it doesn't need any huge power processing units. And thirdly, the plumb or the exhaust which is coming outside the nozzle is uncharged. So it can be used in missions which carries highly sensitive payloads. And finally, it can be used with a wide variety of propellants. Like for example, in this case, we tested with cold gas nitrogen. And so it can also be used with water as propellant, as hydrogen as propellant. So these are some of the advantages. Now, if we take the silicon and flip it over, this is how it's going to look like. So the propellant gas will enter the channel from this side, and so this is the cold gas section, and this is the heater section. So the heater is actually on the top, on the other side of this figure. So when the aluminum gets heated up, the silicon gets heated up, and because of the high thermal conductivity of silicon, we can assume that the same heat temperature can be achieved at the microfluidic channel surface. And here the channel features are a channel width of 50 microns, 50 microns, and channel height of 150 micrometers. And coming to the nozzle section, it was there were only two variants. Either we designed for 10 microns, or we designed for 5 micron nozzle probe width. And the channel depth was the same all throughout the channel section. And a heater section length was designed kept at 2 centimeters in order to provide a fully developed flow towards the nozzle inlet. So this is how the nozzle looks like. So this is a linear slip nozzle because of the MEMS fabrication limitations from MEMS fabrication techniques. So what were the geometrical parameters? So the contraction angle was 15, expansion 20 degrees, expansion ratio was kept at 25, but we kept for the initial design we kept the probe radius sharp. And the probe width, as I said before, we tested for 10 microns and 5 microns. So why did we go for a 10 micron and 5 micron design? So this is a figure showing the predicted stress using a simple ideal rocket model theory which is used for huge rockets, and it is applied for microscales, just to see how it works. So the thrust we predicted is like for a maximum pressure of 5 bars, which is due to the cubesat constraints. We kept the pressure at 5 bars, chamber pressure, and in that such situations we get a thrust of 1 millinewton in case of 10 microns, and we get 5 micronewtons in case of 0.4 millinewton in case of 5 micron nozzle probe design. And the 1 bar was kept as the minimum chamber pressure limit in order to avoid any flow separation in the nozzle, assuming the vacuum conditions. So this is how the thruster was designed. So first of all, we have a double-sided polished silicon wafer, and on top of them we have thermally oxidized oxidation on both sides, and then we coated aluminum on top of this thermal oxidation layer, and then we deposited a PCBD oxide layer on both surfaces again, and then the first dry, the etching was done using a dry deep reactive ion etching technique. So this is the etch through. We etched through completely over here. Then next we had to etch through the inlet channel, which I showed in the schematic diagram before, the inlet manifold. And then we patterned the channel, the microfluidic channel as a third dry step, and finally including the nozzle. So the channel and the nozzle are etched together. And finally we removed the PCB over here, and then we bonded that with the glass or Pyrex wafer. And this is a SEM image of the device, of the microfluidic channel device, and this shows the 50, but the manufacturer is like 49.3 microns, and the probe width of 5 microns. So, and the depth is 150 microns. So this is the fully packaged device. So here is a needle which is used in surgical applications, and it is glued into the inlet manifold, which is using a special kind of glue. And then, so the propellant enters the device from this side, and then if you see, the device is then glued onto a PCB. So how do we heat it? So how do we measure the temperature? So the temperature of the device is measured by measuring the resistance of the device. So and the resistance is measured using a 4-point approach, which means we pass the current from an external source through this port. So we pass the current through the aluminum heater, and we measure the voltage drop across the heater. So by measuring the voltage and the current input, we can measure the resistance, and from there we can calculate the temperature of the device. So and then this is the heater section, and the hot gas exits from this side. So before discussing the test results, I would just go briefly on the test setup. So this is a high propellant, the nitrogen gas is stored at high pressure. This is a pressure regulator. There is a mass flow controller, we can control the mass flow and measure also the mass flow which is going into the system. And this is a valve, and it goes black box is the vacuum chamber, and the vacuum condition could be achieved like 10 millibars. And then here is the pressure, system pressure. Here is the pressure sensor, and we couldn't measure the pressure of the fluid just at the inlet of the nozzle because it's too small to measure. So we had to measure the the pressure at the inlet of the device using a pressure sensor. And then the needle comes, and then the device. And there's an external power source over here, and it provides the current, measures the voltage, and the whole test interface is controlled by a lab interface. Now, test results. Now, first we did the test without heating the propellant. So we tested we measured the pressure. What is the pressure of this in the system against the mass flow rate? So what we see is that there is a linear increase of the system pressure with the mass flow, and also the 5 micron nozzle due to its small flow dimensions is showing a much higher system pressure for the same mass flow, which is logical. But secondly, so as I mentioned before, we were measuring the system pressure at the inlet of the device. So what we did is we calculated the chamber pressure by subtracting the pressure drop from the system pressure. So we had the calculated chamber pressure and the ideal chamber pressure. And we took that ratio, and that was defined as the discharge coefficient of the nozzle. And that was plotted against the throat Reynolds number. And there has been a number of research work based on the losses, the low Reynolds number losses at microfluidic scale. So we could confirm that because you see here, Reynolds number is really low at around like less than 500, and the discharge coefficient in case of 10 micron nozzle was like roughly 70%. So why is the difference? Why is that loss? Because at micro scales, the boundary layer starts forming at the nozzle, along the nozzle wall, and that and the boundary layer occupies roughly 30% of the nozzle exit area. So that leads to a loss in nozzle performance. But in the case of 5 micron nozzle, the discharge CD was like 50% because due to the additional loss due to small throat dimensions. Next, we heated the system, and here, as I said before, the heater temperature is the control parameter. So we control the heater current, and from there we calculate the resistance and calculate the temperature. So the heater temperature is the control parameter, and this is the measured parameter, which is the chamber pressure. And we kept the mass flow the same. This is at 0.35 milligram per second. So for a given mass flow, again we see the system pressure is increasing with increasing temperature. But the increase is not really sharp compared to the coal gas case because the chamber pressure increases only to the square root of the chamber temperature according to the rocket motor theory. And finally, the heater temperature, the electric input power is controlled against the heater temperature. And what we see is that this is for a given mass per 1 milligram. So for 1 milligram per second of nitrogen gas, and to heat it to a temperature of 350 degrees Celsius, it requires our total input electric power of less than 3 watts. So, but the efficiency is really low. It's really low. It's like 15% or it's so a lot, because basically we are heating the structure. So a lot of heat is going in heating the silicon, and then the electricity goes into heating the gas. So this in the next stage of this project, we are thinking of packaging in a better way to reduce these losses. So finally, I have to conclude my work with these conclusions. Like, first of all, we could devise a package which is lightweight, which is 160 milligram, and dimension of 25 times 5, which makes it suitable for use in cubesats. And we could heat the propellant to 350 degrees Celsius with a power of less than 3 watts, and at voltage of 10 volts, which is like within the constraints of cubesats, 10 volts. And specific impulse of 70 seconds at coal gas, and we could increase by 42% when we heat it to 350 degrees Celsius. And we couldn't test the thrust which can be produced with this thruster. So we calculated that it will be somewhere in the range of 100 microns to 1 millinewton. And also this concept can be used for with hydrogen or water in future studies. And also we can confirm that the boundary layer formation plays a major role in microscales, so we need to study further using CFTs and fluidic analysis. Thank you very much for your attention, and thank you for the people's time who have been last time.
We have time for one or two questions.
I understood that your expanded angle is 20 degrees. It's a micronozzle. Did you do any numerical simulation on that?
No.
When you want to choose an angle?
Yes, it would have been because a lot of micropropulsion research work has used a CFD analysis to study exactly what's happening with the boundary layer formation. But due to the limited time within my thesis work, I had to go with a simple theoretical model and just say, okay, let's go with a 20-degree expansion so that we get a thrust of 1 million and lower. But it can be changed. So in the next stage of the project, we can optimize. So just make a change in the device we use for fabricating the MEMS, and then just make it suitable, and you can get any angle you want.
Last question.
Thomas Fiedler from TU Munich. It seemed like that most power was lost by just heating the environment. Did you think of insulating the whole device better for a state-to-state?
Okay, I understand your question. Thank you. So, first of all, I have to be honest with you. I have no background. I didn't have a background in MEMS technology, so I had to work with the MEMS department of TUDelft. So they already had a concept. So this design is just a tool of the design. So due to resource constraints, we couldn't. Yeah, of course, we can go ahead with a better insulation technique. But for the current design, we just kept the system as it is and just made microchannels and nozzles. But in the best approach would be just to heat the gas using microcoil in the channels so that we don't have to heat the structure. So people have done that. I think say in Sweden they have done this with such designs. You heat the gas without heating the structure, so that's more efficient.
Okay, thank you, Mr. Mathew, for this presentation.